All right, there is one function, one exponential function that far outstrips all the others put together in importance, and it is this one. The number e is defined to be 2.78182. It's rather like pi. It is a decimal. That string never ends, never terminates, it never repeats. That string just continues to go on forever. It's an irrational number. It's actually a more technical word. It's a transcendental number. But what that means is, for our purposes, this number goes on. It's rather like pi. Pi is 3.141596, blah, 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 the decimals. E is a little bit more than 2 2/3. This is the value. Which you can look it up on your calculator. You can look in the text. I'm sure you could go online and get the first 100,000 decimals and the expansion of E. But this is the value. It turns out this is the best one. It is not obvious, but this is the best one. Now, the requirement is that. The two requirements are that this is bigger than 0, it's not 1, it is permitted. The difference is this is the best one. And we write this. You don't write 2.71828 blah, 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 blah to the x. You write e to the x. Just like when we write the formula for the area of a circle. You don't write this. You don't write that. It's correct, but no one writes it that way. We abbreviate this long decimal expansion with that symbol. Well, when we write this, you could, if you wanted to, write this as 2.71828 blah, 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 all that raised to the x. A person could do that, but no one ever does that, essentially. I mean, if you wanted to, that'd be fine. But you abbreviate this expression, you abbreviate this number with the symbol E. There are varying ideas as to why E is chosen. But it is, and anyone on earth who knows what you're doing knows what that represents. Anyone on earth who's using e to the x is using e to represent that value. It turns out this function is almost like it's the magic function of the universe. Take any field of study you want to go into. If you model what's happening in the natural world with sufficient accuracy, this number will pop up in those models. If you model the concentration of a medication in the bloodstream as a function of time, this number will manifest itself in those computations. If you string telephone wires between telephone poles or power poles, and the curve, the amount of wire required to string between two power poles, this number will pop up in those computations. If you model the relationship between the predator and prey, as the number of prey increase, the number of predators increase. But as the predators get too many, now what's happening is the food supply is getting small for the prey. Also, there are more predators, so the prey begins to get smaller. As the prey numbers go down, so does the predator numbers. And so then as the numbers get small enough, now there's much more food for the prey, and there are fewer predators, so the prey begins to increase. And so what happens is you have this interaction wave of these two populations. If you map that out and model it to sufficient accuracy, that number occurs in those numbers. If you model the paths of objects orbiting the sun with sufficient accuracy, that number is involved there. It is not obvious this number should be involved in any of those computations, much less that this number should be somehow involved in all of them, and many, many more. If you take a metal beam, and bend it until it reaches its breaking point, this number is involved in those kind of computations. In technology, in biology, in chemistry, this number is involved in all those types of computations and many, many more. That's why this is sometimes called the natural exponential function, because it is so useful in modeling things that happen in the natural world. And to bring this home to something that maybe a little closer to some of us than we wish, when you model the number of people infected by a pathogen over time as that pathogen becomes contagious, this function, this number, is involved in those kinds of models. And so this is fundamentally important in all sorts of types of modeling, all sorts of representation of the natural world. For our purposes, we're going to talk about this function, kind of what properties it has, how to use it, how to do those computations. Now, where this comes from, I've just plopped this down out of the blue sky. Where this comes from actually is Calculus 1. One of the reasons that students have a difficult time with this is that we're talking about ideas that, to really get a deep understanding and a solid hold on what's going on, requires some of the techniques of the calculus. We're trying to talk about calculus ideas without the calculus. That's the nature of the beast. Work can be done with this without requiring the calculus. So what we're going to do is this. We're going to assume that someone else has done the calculus correctly. If nobody else, Isaac Newton did it. And we're going to assume that this is correct and that this function then is allowed because of the requirements. We're going to talk about things how to compute, how to solve equations, how to model certain settings. We're going to talk about using this number and this function. We're going to put off for at least a semester. For some of you, this may be putting it off forever. But until you get to Calculus 1, we're going to put off until then actually developing this from scratch. For us, for now, this is given. This is a function that is permitted to be used because this number meets those requirements. It is an exponential function. Here's how this ties together with our previous work and why I went through this notion of inverse functions. Because the graph of this function, as we saw, roughly looks like this. Every exponential function that we've discussed so far falls into this category. It turns out that this function, roughly speaking, looks like this picture. The details I've left out, but this is the basic shape. In a similar fashion, if someone said, draw a rough sketch of the square function, this would be enough to get the idea across. Well, if someone says, draw a rough sketch of the exponential function, this would be enough to get the idea across. It's not exact, it's not perfect, it's not to scale, but it's the basic idea, just like this is the basic idea of the parabola. Well, this function, notice, this function passes the horizontal line test. Well, we know that if it passes the horizontal line test, that means it is a one-to-one function. That means it does have an inverse function. And that's what we're going to get into when we talk about uniting this with our notions for inverse functions. So for now, this is the value of e, this is the exponential function, this is roughly speaking the graph of it. More to come, but that's the basics so far.